are going fine. You're able to do well. So I'm just here to tell you a little bit more on some of the important questions that may be expected this time in the board exams. So if you practice on these lines, practice these questions, it's going to be a little more helpful. Before I start with those, I would like to give you an overall idea in very short. You know that the board paper consists of broadly three different type of questions. You have objectives, which are generally lower order thinking skills, middle order thinking skills, and higher order thinking skills. Now, why exactly am I stressing on that? The reason I'm stressing on that is because if you focus a lot of your time on different questions and you get stuck, you may actually end up getting lesser marks. Instead, if you follow a little bit of strategy of attempting the questions, that will be much better for you. So you get the reading time. So go through the complete paper before you actually start attempting it. So read through the paper completely, mark out the questions which you know for sure, and then start doing it. You have a case-based section which you should be giving importance, because in that 4 mark questions, they are very straightforward. It's just that you need to understand what is the case, and if you understand what is the paragraph that is given, attempting the questions becomes very easy. Apart from that, there'll be some hot questions which will be not that straightforward, so you have to figure out what is being asked and what are the different steps that you need to apply. Okay, not delaying any further, so I'll share with you some questions. So we'll discuss about them in the form of the solutions also. Okay, so let's start with the first one. So what do we see out here? We see that we have a hollow cylindrical box of length 1 meter and area of cross section is 25 centimeters square, is placed in a three-dimensional figure. Now the cylinder is lying along the x-axis, right? The electric field is given by 50 xi. So since it is given as 50 xi, where E is in newtons per coulomb and X is in meters. Now the most important thing here is that the electric field is directed along the x-axis. Now since it is directed along the x-axis, so we'll have along this direction. So we have to find out the flux for this. For this, at the point P, the area vector, we have to be positive, because the first thing is we need to find out the electric flux. The area vector in this case is going to be positive. For the point A, the area vector is going to be negative. Why? Because it is pointing in the opposite direction. So we'll have a positive flux coming out from the point B, and we will have a negative flux coming out from the point A, right? So let's do a solution for this one. So let me solve this out. So when we do it, so how do we start attempting it? So let me draw the figure first. So this is our x-axis, this is our y-axis, and this is our z-axis. Our cylinder is like this. This is the point A that we have, and this is the point B that we have. Now, we have to find out the net flux. Electric field is given by E, which is equals to 50x I cap. And along with that, we have the area vector. The area vector is 25 centimeters square, so that we need to change that into meters. So how much is that? So delta S is 25 centimeters square. So we'll say 25 into 10 raised to power minus 2 whole square meter square. Why? Because 1 centimeter will be equals to 10 raised to power minus 2 meters. Now, let's try to find out the value of the electric flux. So, first of all, what is the expression that we are given? 50x. A is at a distance of 1 meters, right? Now, since A is at a distance of 1 meter, so the electric field at the point A is going to be equals to 50 I, right? Further, if we talk about the electric field because of B, how do we do that? We'll come to the case of the this thing, the value of B, sorry, electric field at B. Let's try now try to find out what is the value of electric field at B. You have to say that it is going to be equals to, just a minute, let's go back to the question once. Right. The length of this is equals to 1 meter. So total, we have a length of 2 meters because this is 1 meter and this is 1 meter. So total, we have a length of 2 meters. So therefore, electric field at B is going to be equals to 50 into 2. That will come out to be equals to 100 I. Now let's try to find out the flux at A. The area vector is pointing along the negative direction for the case of A. So we will say, how will we find out? So we will say 50 into the area vector is 25 into 10 raised to power minus 4 multiplied by cos 180. We know that cos 180 degree has a value -1. So this will therefore come out to be equals to minus, this will come out to be equals to minus 0.125. Okay, so this is equals to minus 0.125. Now let's try to find out the electric field at the point B. Along with that, if since we are talking about in physics, so we need to be careful about what is the unit. So it's going to be equals to Newton meter square Coulomb inverse. Phi at B is going to be equals to 100 multiplied by the area, that is 25 into 10 raised to power minus 4. Electric field and the area vector, because electric field is like this, and this point the area vector is here. At this point the area vector is in the at it inclined at a direction of 180 degrees, right? So this will be equals to cos 0 degrees. So if this is cos 0 degree, what will we get? So this comes out to be equals to 0.25 Newton meter square Coulomb inverse. So we have got these two fluxes, right? Now, since we already have the flux, we need to find out the net flux coming out. So the net flux will be the summation of flux from A plus the flux from B. So what will we get because of this? So the net flux, if we say, that's going to be equals to phi A plus phi B. So that comes out to be 0.25 minus 0.125. So therefore, this comes out to be 0.125 Newton meter square Coulomb inverse. So this will be the net value of the flux. So that answers our first part. Now let's go back to the next part. So the flux we have got. Therefore, the next thing that we have, if we now go to the we already got the value of flux as equals to 0.125 Newton meter square Coulomb inverse. So therefore, phi being equals to, again writing it, E dot ds equals to Q upon epsilon naught. So therefore, Q will be equals to epsilon naught into phi. Now let's substitute the values. So it is 8.85 into 10 raised to power minus 12. So what will we get because of this? So let me substitute that. 8.85 into 10 raised to power minus 12 into the flux, which is equals to 0.125 Newton meter square Coulomb inverse, right? So using this, you can figure out how much is the value is going to be. So that tells us about the value of this, the answer for this one. Hopefully this is clear. Now, let's move on to the next question. So what is the next question? Let's see. Now, this is slightly tricky, if you may say. What are we given? We are given that S1 and S2, right? So S1 is the inner sphere shell and S2 is the outer shell. These are concentric thin spherical shells. That means both have a center which is same, and they enclose the charges Q and 2Q. Okay, so S1 encloses charge Q, S2 encloses charge 2Q, as it is shown. You have to find out the ratio of the electric flux that is coming out through S1 and that is coming out through S2. So again, we have to use the concept of electric flux in this part as well. Mind you, here the charge enclosed are different, but the flux that we are going to find out will include both of them. So what will we do as a result? Let us solve that to see it. Okay. So going back to the question, we have these two fluxes. Just a minute. These two spheres to be precise. Let me just draw that. This is one sphere. This is your other sphere. And this encloses charge Q. This encloses charge 2Q. This is your S1 and this is your S2 that we have. Okay. Now, let's go ahead. S1 has a radius which is equals to R1. This has a radius R1 and this has a radius R2. Okay. Now let's talk about the flux. So we know that flux, which is we have already discussed in the previous question. The value of flux is equals to integration of E dot ds, which is effectively equals to Q by epsilon naught. So the flux is equals to Q by epsilon naught that we have, right? That is how much is the charge enclosed divided by epsilon naught. Okay. So if we talk about how much is the flux from the inner shell, so phi 1. So there is only a charge Q that is enclosed. So it becomes Q by epsilon naught. If we talk about the flux coming out from the outer sphere, so the outer sphere has a charge, an additional charge to Q also. Now, this is where it becomes interesting because the inner charge is not only, it's a shell. So the charge is going to be there on the surface of the shell. So you cannot limit that that particular charge will only be resulting into a flux inside the sphere 1. It's also going to be influencing the outer sphere, right? Okay. So therefore, the net flux that's going to come out from the outer sphere will be a combination of charge Q coming from inside and charge 2Q coming from outside. So that gives you 3Q upon epsilon naught, right? So this would be the net value of charge that we have. So now this becomes very easy. You can now take a ratio. This is a very easy question. You should be expecting a question similar or this one of around 3 marks. So now from here, it is easy. So phi 1 by phi 2, if you take it, so the ratio of these two will come out to be of the order of 1/3, right? Okay, so this is the first part. Now let's go back to the question. So we have already got the ratio of the electric fluxes. That comes out to be equals to 1/3. Now going ahead further, if we say that, how will the electric flux through the shell S1 change if a medium of dielectric constant 5 is introduced in the space? Now this is interesting. You need to understand. You would have studied that in capacitance, right? That if you include any other medium having a higher value of dielectric constant, right? That the any presence of a dielectric constant basically increases the possibility to store charges. So the charges, more amount of charge can be stored if you have a higher value of dielectric constant. So more is the dielectric constant, more can be the amount of charge that can be stored inside it, right? Okay, so let's try to figure out how exactly this is going to change. So in this case, we are given that in this particular medium between them, you are introducing another dielectric constant. Okay, so if you do that, so what will we get? So this flux is definitely going to be introduced. Means capacitance increases because of the introduction of dielectric, but dielectric being a medium having, it is not basically a conductor. It's a kind of a semiconductor and insulator kind of a medium. Because of that, it does get influence. It is a way to store charges, but the amount of charge that will be available actually comes down. So we will say that the flux will actually come down. Why? There are different ways of understanding the same thing. Let me explain you how. We know that, let me change the page. So we know that the flux is equals to Q by epsilon naught, right? Now, because of the presence of a dielectric, what it does, if you just imagine what's a dielectric. Dielectric is basically a medium which is not free, right? There are charges in it. Now, because it is not free, epsilon naught will no more be there. The permittivity will now be multiplied with the relative permittivity, right? That is the dielectric constant. So we will say now the net flux will be equals to Q by epsilon naught K. K represents the dielectric constant. So what will we get? So effectively, this is nothing but phi over K. Correct? Now, since this is equals to phi over K and the dielectric constant that we have, that is equals to phi, so we will get phi divided by phi. So the new flux actually becomes less. The net amount of electric field coming out from this conductor decreases by a factor of 5. Correct? Okay. So this is about this question. This is, you can say, a kind of a tricky question which involved the concept. It's a kind of a hot question. That's the reason I have included that. It's a straightforward question, but it's just that you need to understand how the dielectric, because you may wonder, dielectric is a topic from capacitance. How exactly are we dealing with here? It's a flux. So just understand, dielectric basically means that it is any other medium. So permittivity is going to change. That's the reason in capacitance we say that it has more capacity to store more charges. So you can store more charges, but because of the storage of more charges, it becomes more denser. And because it becomes denser, it is not easy for the electric lines of forces to come out or the flux lines to come out. So the flux actually decreases. Okay. Fine. Now we come to a very standard this thing, derive an expression for the capacitance of a parallel plate capacitor with air present between the two plates. Now, why exactly I picked it up? Because these are some questions. These are standard questions, these are expected questions this year. So if you do these standard questions, it will be very easy for you to score marks, because these are very basic standard concepts that you can apply and you can get marks in that. So when we are talking about a parallel plate capacitor, right? So a parallel plate capacitor is simply like this. So what you do, you connect the two ends across a battery. So there is a potential difference that you're introducing because of this. correct? Now, because of the introduction of the potential difference, what's going to happen because of it? We will say that there is going to be a charge here, because this plate, let's say if I mark this plate as A, this plate as B, so there is going to be a charge here. So this is going to be positive charge, and this plate will have a negative charge. Because of this, there is going to be an electric field that will be set up, correct? So if there is an electric field that is set up, so what is going to happen when there is an electric field? How do we define the electric field? Further, if I say that the distance between these two plates is equals to D, so the potential difference that we have is being applied across these two ends, right? I hope it makes sense. Now, if we talk about this, just a minute. Okay, so sorry for that. So if we talk about this, so we have an electric field that is being set up because there is a potential difference that is applied across the two ends of the capacitor, right? So there is an electric field. Now we know that electric field, we can say that it's equals to V upon D, or you can say V is equals to E into D. Now, what is the electric field? How do we define it? Electric field at it, because if I say that there is a charge that is present out here, so there is going to be an electric field because of this. You would have studied that electric field is equals to sigma upon epsilon naught, right? Now, because there is sigma upon epsilon, now what is sigma? Sigma is charge per unit area. So we can say that this is equals to Q upon epsilon naught A, right? So using this, if we just substitute for this, so what will we get? We will get Q upon epsilon naught A into D. This is V, correct? So let's rearrange this particular part. This is the electric field for a set of parallel plates. So using this, if we just rearrange this part, can we write it as Q equals to epsilon naught A by D into V? We already know that the charge that is there on each plate depends upon how much is the potential difference that we have applied. So we will say that the charge is proportional to the potential difference. And here we have already got a relation between them. So what is the relation? So therefore we say that the proportionality constant is capacitance C. So C becomes equals to epsilon naught A upon D. So we get the capacitance as equals to epsilon naught A by D. Now, mind you, here we are assuming that there is only air that is present between the two plates. Because there is only air, so we have taken it as epsilon naught. If it also asks that if you have to modify this expression to take care of the dielectric also, so what will you do? You'll multiply this expression of C, which is equals to epsilon naught A by D, by the dielectric constant. That will give you the net capacitance in the presence of a dielectric. As I talked in the previous question, the capacitance will increase because of a higher dielectric constant, right? So this is the first part. There's very simple thing, 2-mark question. It's a very easy, straightforward 2 to 3 marks, you will get it. Okay. Now let's move on to the next part. Now it says obtain the equivalent capacitance of the network shown. Okay. For a 300-volt supply. Now the first thing that we'll observe and say that, okay, this C4 is in parallel with these two, and these two obviously are in parallel with this. But is that actually true? Let's try to figure that out. So let me draw this and explain it to you that that is not the case. So what we have to do in this case, let me just put up the picture and explain it to you one by one. Okay, so we have a capacitor here, we have capacitors here, we have capacitor out here, right? And Then we also have a 300-volt supply. This is 300-volt. Along with that, if you say 100 picofarad, 200 picofarad, okay. This is 100 picofarad, 200 picofarad, 200 picofarad, 100 picofarad, C1, C2, C3, C4. Okay. This is C1, C2, C3, and C4. Okay. So we have got this. Now using this, let us try to figure out what exactly is the net capacitance. Let's see how does it work. Okay. So let us redraw this picture. So if we redraw this picture, just a minute. Yeah. So let me redraw this. So first of all, you can see that these two are connected in series. So let's try to find out the C series part. So 1 by C series will be equals to 1 by C2 plus 1 by C3, right? So from here, what will we get? We'll get 1 by 200 plus 1 by 200. I'm not taking the units as of now. This becomes 2 by 200 or 1 by 100. So C series, I can say that's equals to 100 picofarad. Now that 100 picofarad is in parallel with this C1. So effectively, if we just do that part also, the C parallel can be written as C1 plus C series. So therefore, there will be equals to 100 picofarad plus 100 picofarad. That comes out to be equals to 200 picofarad, right? So that results into a circuit like this. This is 300 volt. This is 200 picofarad. And this is 100 picofarad. Now you need to understand one thing, that these are not in parallel. How? I'll tell you that. You can redraw this circuit and say that this is C net and this is C4. So you can simply see this, sorry, that this is one and this is your other, and they are connected like this. This is your 300 volt. It is a trick question because it is given in that particular fashion. So therefore, this is your, let's say, C net and this is your C4. So because of this, this becomes your 200 picofarad. This becomes your 100 picofarad. So what is the net capacitance? These are in series. So we'll say 1 over 200 plus 1 over 100. So that becomes 3 upon 200. That is 1 over C net. Remember to take its inverse also. Many students do forget about that. Remember to take its inverse. So C net, therefore, will be equals to 200 by 3 picofarad. So this is the net capacitance, right? So always, whether we'll be discussing some questions on Kirchhoff's law also, that is for current electricity. So always don't just look into the figure. Try to figure out which ones are in series. So if you just take a string and take it around, correct? Imagine that you're taking a string and taking it around. If there are branches, the string is going to branch out. If there are no branches, if it goes straight, that means it is in series. Okay. If that is not, just don't look into the figure that is given. Like, so like you have in organic chemistry, you have long chains and so on. You have to figure out which one is the longest chain. Similarly here also, you have to figure out which one is your straight chain, a straight wire, correct? So we have got the net capacitance. Now let's go back and see what else do we need to find out in this question. The charge on each capacitance. Now, since you know how much is the net capacitance, right? So we can always figure out how much is the charge. How do we do it? Because Q equals to C into V. Okay. Now the charge is going to remain the same in series, but it's not going to remain same in parallel. Correct? Okay. So whichever ones are in series, the charge will remain the same. So let's try to figure that out. So total charge we'll first figure out. So total charge will be Q, which is equals to C into V. This is the C net into V. So that is 200 upon 3 picofarad into a voltage of 300. So this goes off. Now, since it is picofarad, so picofarad will be 10 raised to power minus 9, right? Okay. Yeah. Sorry, 10 raised to power minus 12, my bad. 10 raised to power minus 12. So therefore, what will be the net charge? The net charge will be equals to, we have 10 raised to power minus 12. There is 2 and 2, 4. So therefore, this will become 2 into 10 raised to power minus 8 coulombs. So the net charge that will be flowing through it is going to be 2 into 10 raised to power minus 8 coulomb. This charge will flow through C4. So the charge through C4, Q4, will be equals to 2 into 10 raised to power minus 8. Now there is going to be distribution of the charges, correct? So for that, we have to find out how much is the potential drop across each one of it, correct? Okay, so let's see. The potential drop, if you want to find out the potential drop across this C net, because that is a parallel combination that we have, correct? So what is the potential drop across C net? So V will be equals to charge is known. So the potential drop across the Cn, if you want to find out, how do we do it? Q equals to Cv, right? So Q by C, charge is known, 2 into 10 raised to power minus 8. That is the total charge. How much is the capacitance? Capacitance is 200 into 10 raised to power minus 12, right? Okay. So therefore, how much does this come out to be? This comes out to be equals to 100 volt. So the potential across this is equals to 100 volt. Now what is that? That means the net potential across this part is 100 volt. The net potential across this part is also 100 volt. Correct? Okay. So let's now try to find out how much is the charge in C1. C1 is 100 picofarad, right? So 100 into 10 raised to power minus 12. Voltage is 100 volt, correct? So therefore, how much will we get? We get 1 into 10 raised to power minus 8 coulomb. Now you want to find out how much is through this. So through this also, if you remember, we got the net capacitance as equals to 100 picofarad again. So the net charge that is flowing through Q2 will also be equals to Q3 will also be equals to 1 into 10 raised to power minus 8 coulombs. So this way we find out, we break it down. Always remember, we have to find out the net potentials when you have a distributed circuit. In series, the charge is going to remain same. Similarly, in case of current electricity, the questions, you will say that the current remains same. In parallel, whether in capacitors or in current electricity, the potential will remain same. So you have to break it down, figure out how much is the potential drop across each, right? In parallel, the potential drop will be the same. In series, obviously, each capacitor or each resistor or each inductor, there will be a particular amount of potential drop, right? Okay. I hope you have followed it so far. Now, let's move on to the next question. Now, this is a type of question which you should always try to make it into the form of a Wheatstone bridge. See which ones are in series, which ones are in parallel, right? And which capacitor corresponds to P, Q, R, and S, right? So so you can clearly see that R and S is the centermost. So if you replicate the Wheatstone bridge of current electricity, so the galvanometer, the role played by galvanometer, you can clearly see that it is here, right? So what you should do is that, let's say this is your point A. I'm going to draw it separately, but let me again explain it here. Sorry. So you have one capacitor, you have another capacitor, you have another capacitor, you have another capacitor, right? And if you say that this is what you have, this is your point B. Okay. Okay. Now from point B, from point A, there are there is one resistance out, one capacitance out here, correct? Which is connected to the point P, and P is connected to S. So let's say if I say this is R and this is S, correct? Okay. If we take that, then we need to also figure out where are the points P and T. So let's say this is P, this is T. Okay. Now let's do it further. So between P and R, you have C2. Between R and S, you have C3. Between R and T, there is no capacitance. So this is joined. Nothing is here. Similarly, between P and S, it is joined. No capacitance. Correct? You have between S and T, and there is a capacitance here, and there is a capacitance here. Correct? So now you can clearly see that it's not a balanced Wheatstone bridge, right? But having said that, you can clearly see one more thing. R and T are at the same potentials because there is no potential drop between R and T. There is no capacitor. There is no potential drop, right? So we'll say that R and T are at the same potentials. P and S are at the same potentials, correct? So effectively, what you have that this point and this point are same. So therefore, the starting point of C2, C3, and which is this SNT, C4, all of them are same. Similarly, the ending point R, which is the same for C2 and C3, is also the same as C4. So therefore, C2, C3, and C4 are in parallel, and that net combination is in series with C1 and C5. So if you identify it, if you look at it and say that, okay, this is such a big circuit, how will I do it? That will become very difficult for you, right? So this way, it is just a matter of a few minutes to figure out what exactly are the points, right? Just a minute. Yeah. So now let's try to solve that. So let's now try to solve that and figure out what is the net capacitance that we have. So as I said, this is C1, then we have C2, we have C3, then we have C4, we have C5. This is point A, this is point B. So C1, C2, C3, C4, and C5. Okay. Along with that, now let's try to connect it. We have P, R, S, and T. So this is your point P. Then you have R, S, and T. So from here, what will we get? Let us also draw the points. P and S are joined together. R and T are together. Okay. Now, if we go ahead further and say this. Just 1 minute. Yeah. So if we go ahead further and talk about this, as I told you, so we will redraw this picture in the form. This is one capacitor. This is a second capacitor. This is a third capacitor. This is a fourth. This is A. This is B. This is C1, C2, C3, C4, C5. Okay. Further, if we do this, so we will get something like, just a minute. We have each capacitor of 2 microfarad. So we'll have C2, C3, C4. So total they are in parallel. So therefore, you can just add up C2 plus C3 plus C4. So it will be 2 plus 2 plus 2. So that will be equals to 6 microfarad. So therefore, we can reduce this picture to a following picture. That is, this is C1. This is your 6 microfarad. And this is your C5. And this is your B. So the net capacitance, so 1 by C net that we have, that is equals to 1 by 2 plus 1 by 6 plus 1 by 2. So it becomes 3 plus 1 plus 3 divided by 6. So 6 plus 1, 7. So the net capacitance will become 6 by 7 microfarad. So this is as simple as that, right? Okay. Next, we have to find out the total charge enclosed and the energy stored. Let me go back to the question and show that to you. Okay. Next is, it says, if a DC of 7 volt is connected across AB, how much is just charged on from the source and what is the energy stored, right? So the charge is going to be Q equals to C into V. Capacitance, we have already got it to be 6 upon 7 microfarad. Voltage is 7 volts. So therefore, this becomes 6 microcoulomb. And energy is equals to half C V square, right? So what will we get? The total energy, the total capacitance is going to be equals to 6 upon 7 microfarad multiplied by voltage is 7. So that is 49. So this becomes 3. This becomes 7. So we will get 21 microjoules of energy, right? So that is 21 into 10 h per minus 6. Okay. Then now let me go ahead and talk about the next question. Here we are given using Kirchhoff's law, calculate the current through the 40 ohm and the 20 ohm resistors in the circuit, right? So what will we do in this case? So we have to identify the loops, right? There are two loops, correct? And there are two rules also, the Kirchhoff's law. One is the junction rule, right? So according to the junction rule, so if you have multiple currents, I'll just reiterate on that. So let's say you have multiple currents, I1, I2, I3, I4, right? So you have three currents which are getting in and one is going out. So we'll say I1 plus I2 plus I3 minus I4, that will be equals to 0. Okay. So the total sum of currents at a junction is going to be 0. Similarly, within a loop, the net potential is going to be 0. Correct? Okay. So let's talk about the loop out here. Generally, by convention, we say that if there is a common resistance, the current direction through each of the loops should be the same. It should ideally not be different. Okay. So we have these two loops. Let's say this is our loop 1 and this is our loop 2. Correct. And using this, we can figure out how much is the current that is drawn. So let's say the current that is drawn from here is I1. The current that is being drawn from here is I2, correct? So through this, you will have the current that is flowing will be I1 plus I2. Now, what all are going to be the values? So what are the equations that we'll have? Let's see. So for the first loop, we will say we have 80 minus we have 20 I1, right? And now if you see the direction of current we have taken through 40 ohms is towards right, okay? So, and we are entering that point in an opposite direction, correct? So we will take it to be positive. So plus 40 into I1 plus I2, which will be equals to 0. For the second loop, if we say this, so we will have the current, okay. Now the current has to pass like this. So 40 plus 40 into I1 plus I2, right? Minus 10 I2, that will be equals to 0. Okay. Now using these two, we have to figure out. So there are two set of equations. You have to write down in terms of an I1 and I2. Once you, because there are only two variables, I1 and I2, using that, you can simplify it and figure out what is the value of I1 and what is the value of I2. Okay. Now this question, you may feel that again a question on Kirchhoff's law. No, this question does not need anything. You do not need to use Kirchhoff's law at all. Let's explain you how and why. So here, what we have is the following. You have to find out, you don't need to use Kirchhoff's law actually. You can just use the junction rule, one loop equation and you're done. Nothing else to be done here. Okay. So use Kirchhoff to determine the potential difference between the points A and D when no current flows through BE. So when no current flows through BE, that means what? It is open circuited. This is going to be just the potential that you have to take into consideration. You have to find out between A and D. Okay. So which loop you will take? You should always take the loop which has the smallest resistance. So you will go according to this, this, and this. Okay. So what will we get? We will get VA, potential at A, minus 6. 3 is also along the same direction, right? Minus 3. Along ED, there is no potential drop. So minus 0. This will be equals to BD. Mind you, this is a question of 3 marks, right? So it is just pure logic. You do not need to do anything else. If you just put it, you're done. If you want to do it using Kirchhoff's law, you can do it. No problems. You can take a loop out here. You can take a loop out here and solve the two. And then put the current through BE as 0 and you will get the same value. But ultimately, it will come out to be the same thing, right? Okay. Now, here we have two small identical circular loops marked 1 and 2 carrying equal currents are placed with the geometrical axis perpendicular to each other. Find the magnitude and direction of the net magnetic field produced at the point. Okay, so let's solve this one. Okay, so in this case, what we have, let me draw it. So if we have this and we have this, so further, if we talk about this, this is X, this is X, right? Okay. and these two are carrying equal currents, and this is at 90-degree angle. Okay, fine. Now, if we go ahead further in this, so how do we approach it? Let's try to understand the approach towards this question. So you have two identical loops which are carrying equal currents, and they're placed in the geometrical. Find the magnitude. So there is a loop 1 which is carrying a particular amount of current, and because it is carrying a particular amount of current, there will be a magnetic field produced because of this, right? So there will be a magnetic field which will be produced as a result of that, and similarly there is going to be a magnetic field that will be produced because of the bottommost coil. Okay, now what is going to be the magnetic field that will be produced? So let me just also mark. Okay, this is point O. Let me mark. This is point O, and this is loop 1. This is your loop 2. So because of loop 1, and is there anything else that is given? No. Okay. So because of this, if we just try to say that the radius is R, capital R, of each of the loops, and this distance is X. So the magnetic field, if we write it down, so that's going to be given by mu naught divided by 2 into, here we have R square plus X square, right, to the power 3 by 2. So we will get something like 3 by 2 mu naught into I into R square. So this is going to be directed. The magnetic field is going to be like this. And similarly, you will have a value of the magnetic field along the perpendicular direction, right? Okay, just, yeah. So these two will be two perpendicular directions in which the magnetic field, the magnitude is going to remain the same. Okay, so one is going to be, so if I say this is C1, this is center C2. So one is going to be along OC1. So this is from the loop 1. From the loop 2, it's going to be equals to mu naught by 2 I R square upon R square plus X square to the power 3 by 2. Now these two are along perpendicular directions, right? We have to find out the net value. So the net magnetic field is going to be equals to square root of B1 square plus B2 square, right? The magnitude are same, so we can just take that factor out. Mu naught by 2 I R square upon R square plus X square to the power 3 by 2 into root 2. Okay, so this is the net value of magnetic field. So this gives us the total value of magnetic field. Now for this, if we go back to the question, find the okay, now if you take an approximation that it is small, then you can just take different values of the value of X, that is X being more as compared to the radius R, then you can ignore the factor of R square in the denominator, and that's going to give you the net value of magnetic field. So broadly speaking, these are the important questions that we have picked up, right, through discussion. Obviously, we'll be sharing many more questions here by today so that you can practice. These are all going to be important questions. These are from past year question, this year sample paper question also, and we expect that these are going to be the questions that will be asked in the current board exams. So on that note, we end it here. Hope you liked the session. Hope it was useful, and stay tuned for many more such for sessions, and we will be discussing more. And if you still feel that you need some help regarding any concepts, any topic from physics, chemistry, maths, bio, please let us know, and we'll be more than happy to help you out in that regard. Yeah. Thank you. Have a good day. Have a great exam. All the best. Thank you.